Yeah, as you can see in the lecture material that I have shared with you early this morning. So today we will discuss about another method to collect data. So perhaps if in our last lecture we discussed about how to collect data through survey. So today we will discuss how to collect data through another approach, that is through experimental design. So let me share my screen. As you can see on the screen, right? This is another data collection method. This is lecture number 10. It should be week 11, but since there was a public holiday last week. Okay, so another method to collect data, we call it experimental design. So perhaps if you pay attention on the last lecture material, how to collect data through survey method. So this technique, the way how to collect data through survey is very common to be used in social sciences, right? So basically the data is already available around us, but the way how to collect data through survey, through questionnaire, so that is similar to what we are going to learn today. When you are in the field of, for example, of food science, or maybe veterinary medicine, so of course you can also collect data. Perhaps later on in the end of your study, you need to do like a final year project. So in which perhaps you need to do a kind of experiment. So usually the experiment that you are going to do, the way how to collect data in your research is through experimental design, right? So that is the topic of our lecture today. So the topics of this lecture material is what is the definition of experimental design and the objective of conducting an experimental design, basic principles of experimental design, some terminologies that you need to be familiar with, and then types of experimental design, and perhaps we are going to discuss a very simple kind of experimental design, that is a one-factor experiment in completely randomized design, or sometimes we call it as CRD. Okay, so let's start with the introduction or definition and so on. So as you can see here, okay, experiment is one type of data collection method which is very common in the field of science, food science and industries, veterinary medicine, in medicine itself, and many other fields, right? So when you, for example, conduct this kind of experiment in a lab, right? So that is basically the way how to collect data, because when you do a kind of experiment like this, right? So in the end, you need to do measurement. When you do measurement, so you have a number that is the data. So that is why experiment is another type of data collection method. So when you do a kind of experiment, let's say you want to conduct an experiment to see the effect of concentration or the effect of dose on, let's say, blood pressure, effect of dose on blood pressure, for example. So later on, in that kind of experiment, perhaps you need to use experimental observation. Perhaps very common to be used is, let's say, mice, right? You conduct experiment to see the effect of dose on blood pressure. So let's say you use a mice as an object of your experiment, right? So after you give some treatment on the mice that as the object of the experiment, then in the end, maybe after some times, you will do measurement. The measurement you do is you measure their blood pressure. So the blood pressure that you measure we call it as a response. So the response is something you measure from a kind of experiment. So the data obtained is the response. So this is measurement basically of the experimental object that has been given a treatment. So as I have explained to you, to see the effect of dose on, let's say, blood pressure. The object of the experiment is mice, and then you do or you measure blood pressure on the mice. So the mice are the experimental object, and then the treatment you apply is to give some dosage to the mice, and then you measure the blood pressure. So the blood pressure is the response. So if you conduct an experiment, you need a design, right? Actually, you can do a trial and error. Trial and error is also an experiment, but it is very good. It is better if you conduct an experiment by arranging the experimental object and so on, so that the experiment will be more efficient. So it means that experiment need to design. You need to design your experiment in order to obtain valid data. Again, even if you do using trial and error, let's say without any design, so you only trial and error, it is also an experiment. But what we are going to learn, so what you need to do, right, actually to design your experiment to have a more valid experimental result, so that the conclusion obtained are accurate, or sometimes we call it as not biased, and it has a high precision as well. This is also level of accuracy. So that is what we want to learn. So experiment needs a design. So design of experiment, we call it as experimental design that we learned today. So some components of the experiment is, related to this is like data, right? So data actually not yet available until you conduct an experiment. So the experiment is the way how to generate data, generate a response from a treatment, right? So because if you don't do an experiment, the data is not available. Not like in survey. In survey, actually, the data is already available around us. When you use a questionnaire, actually that is the tool to catch the observation that is already available. But in experiment, the data is not available until you conduct an experiment and then you do a kind of measurement. Okay, that is in experiment. So this one, in survey, if you read here is actually the data is already available as I explained to you. But in experiment, not yet available until you conduct an experiment. So only need to collect the data. So that is the difference between the way how to collect data through experiment and through survey, as what we learned last week in our last lecture. About the object of the research. In an experiment, that the object condition should be homogeneous. If you conduct an experiment, you do anything so that the experimental object that you use, you try to have the experimental object as homogeneous as possible, so that you will see the effect of treatment more accurate, because you do something so that the experimental object is homogeneous. For example, if you use mice in your experiment, so you try to select mice as homogeneous as possible. Homogeneous in terms of maybe weight, homogeneous in terms of perhaps age, and maybe a species, and so on. So as homogeneous as possible. But of course, in social sciences, in survey, of course, the object will be not homogeneous. The condition varies, right? If the experimental object are human, right? Of course, you will have a very homogeneous condition of human, like that. Okay, then the next one is an action was given in form of treatment. So that in an experiment, you need to apply something to the experimental object. That is, we call it as treatment. But if in the survey, right, in social sciences, usually we don't do any treatment on the experimental object in general, not all. Right? In general, we don't give any treatment on the experimental object. Usually we just do, we observe or we catch information available. Okay. Meanwhile, regarding environment, right? Regarding the environment, so in experiment there is a control of environmental condition. If the condition of the environment is not homogeneous, right? So we can control the environmental condition. But of course, in social sciences or in observation, a survey, so usually there is no direct environmental control. But in experiment, we can do that, right? For example, if you do an experiment in a lab and so on, you can make, let's say, the temperature as homogeneous as possible. That is environment. But in, for example, survey or observation, of course, it is not easy to do that, right? Okay, let's go to the next one. Yes. So actually, what is the experimental design? After my explanation before, so we can formulate the definition of experimental design. So actually, it is a test or series, right? Test or series of tests in which it has a purpose changing. Which purposeful changes are made to the input variable of a process or system, so that we may observe and identify the reason for changes that may be observed in the output. So it means it is a test or series on the input, right? On the input variable, and then it has a process. So input variables, perhaps something that we can control. So it can be related to experimental object. It can be related to the treatment that we want to apply. And then, of course, it has a process, right? It has a process. So here we do something on the process. So that, and then we will see the output. So it is just like input, process, and output. And then we will see the response in the output. So we do measurement on the response, right? So it is a planning experiment to obtain information relevant to object of the study. Maybe later you will have more detailed explanation if the definition is unclear, right? Thus, the experimental design includes several methods, right? So first, it includes determination of tests or series of tests, which are later referred to as a treatment. So, of course, later in the experiment, you need to determine the treatment, right? The second one is, it is a process of arranging experiment in the field. So the field here in general meaning, because it can be in the field, really the field, which is outdoor. It can be in a lab. So the field here is in very general meaning. So process of arranging experiment. And then it is also the process of measuring the response. So look at this, it involves to determine the treatment, to arrange the experiment, and it includes the process of measuring the response, which is the effect of the applied treatment or the test, right? So again, experiment needs a design so that we will have a more accurate result. Let's go to the next. Okay, this is related to the previous slide, right? So as you can see here, it involves input, process, and output. So in general, input is related to experimental object, and then on the experimental object, we apply treatment. Right? We apply treatment. So the treatment we apply here is it can be a control treatment. That is, we call it as control factors. But the process here can be influenced by uncontrolled factors, right? So we can focus here. But of course, it has some, this one, the uncontrolled factor, have some influence. So for example, if we want to see the effect of dose on the blood pressure, for example, effect of dose on blood pressure. So of course, the dose is the control factor, because we can control the dose. We apply the dose on the experimental object, so that is in the process. But of course, we must realize that many factors have influence on the blood pressure. So perhaps the weight of the mice, right? Perhaps the species of the mice. This is uncontrolled. It is uncontrolled, right? But what we can do is the control factor. So whether they are control factor or uncontrolled factor, it will have influence on the process. Then later on we measure on the output. So this is another example, right? Let's say the input is, let's say the in the let's say agricultural field, right? So the experimental object or the input can be certain commodity crops, like perhaps rice or maybe corn, cassava, and so on, right? So the control factor, if you conduct an experiment with the experimental object of this, right, it can be fertilizer, right? It can be the spacing between plants. It can be spraying frequency. It can be varieties of the crops, right? It can be the cultivation patterns. And it can be anything, right? So these one are the control factors. But what are the uncontrolled factors? It can be like wind speed, right? Because wind speed may have influence on the plantation. It can be rainfall, it can be fertility of the soil, it can be humidity, it can be temperature, and so on. So all of those are uncontrolled factors, and they may have some influence on the result, right? So what we focus on is this, of course, and the uncontrolled factor we can do something so that the effect can be localized. And in this kind of experiment, let's say the output is, let's say, plant height, right? Plant height, or maybe leaf area, right? Or maybe the diameter of the stem, production component, and then the yield, and so on. So this is a very good example to give you an illustration of the components of this experiment. Let's go to the next. Okay, what is the objective of the experimental design? Few objectives of conducting experimental design: by arranging experiments, or by selecting or determining the treatment, and so on. Okay, so the first one is choosing the control variable or control factors that has most influence on the response. So we need to determine, right, the control factor that may have the highest influence on the response variable. Of course, perhaps you will have many X, right? You will have many control factors. After conducting experiment, you will be able to select out of these control factors, what are the most important factors. Let's say you do a kind of experiment to see the effect of those, that is X1. Let's say types of fertilizer, and then variety of the crops, that is the third factor, and so on, to the plant, let's say, yield of the crops, right? In the end of the experiment, you will be able to determine what are the factors that has most influence on the yield. The second one is determining where to set the influential control factor, so that the Y, that is the response, is almost always near the optimum. It means it is to determine the optimum setting. Not only selecting the control factors, but also we can determine the optimum setting of the control factor. So you can see the difference. If here the first objective here is to select the most influential X, right? But here on the most influential X, we can have the optimum setting, the optimum value. Okay, the third one is to determine where to set the influential X so that the variability in Y is small. Another objective is this: we always want to have Y is as stable as possible, so that by conducting an experiment, we can determine the X that give the smallest variability in Y. right? It means we can determine the x or the value of the x itself, right, to have the most stable y or most stable response variable. And the fourth objective is that to determine where to set the influential x so that the effect of the uncontrollable variables are minimized. Okay, so that is the fourth objective. So I believe this one is very clear. Selecting the x, right? Selecting the most influential x, then to determine the best setting of the influential x, and then number three is to determine the most influential x to have the minimum variability of the y, and then to determine the setting of influential x so that the effect of the uncontrollable variable are minimized. So this is how to control the uncontrollable factors. Okay, as you can see here, in conducting experiment, we need to understand more about the basic principles in experimental design. So few basic principles in conducting experimental design, so that later on if you conduct an experiment, so you need to consider these basic principles. So the first one, right? The first one is randomization, right? So maybe let me just go here. So the first basic principle is randomization. So let me arrange this one so that I think that's the same. So let me maximize. I think it will be the same. So the first one is randomization, right? And then the second one is replication. And then the third one is local control. So what is the randomization? So each experimental unit, right? Each experimental unit, so you can imagine this is like an experimental object. Each experimental unit has the same chance to have a treatment. So it means you need to apply treatment on the experimental object at random. Okay. So maybe let's see here, if I apply the treatment to each experimental unit, to each experimental unit at random. So that we can remove any subjectivity method. So not subjective, because we apply the treatment. I think this one. You apply the treatment to the to each experimental unit at random, right? So let's say which dose will be applied to which experimental unit should be arranged at random. So we apply the treatment to each experimental unit at random, right? So this is the first basic principle. We call it as randomization. The second one is replication. So the application of treatment to several experimental units. So I think let me provide more clear words. So each experimental unit receive treatment more than one time. Or similar to that, or that one is also okay. So let's say each treatment, I think that one is also okay. Let me see here. Treatment is applied to several times. Is applied to like this also okay, to several experimental units. something like this. So treatment is applied to several experimental units. So as you can see here, let's say a certain dose is applied to more than one experimental unit. So we call this one as a replication. So that if you have this kind of replication, so you will have a more accurate result because you do replication. So if everything is possible, right? Let's say you have enough budget, you have enough resources. So if it is possible, then you do this experiment more than one time, right? And then the third principle, third basic principle in experimental design is we need to do control of experimental conditions that have the potential to affect the response of a treatment. Treatment. So what I mean here is any other things beyond the treatment must be what we call, we need to make other than treatment, we make anything must be homogeneous. So right, so that if that is, we call it as local control. So for example, if you conduct an experiment to see the effect of dose on blood pressure, so you must make sure that the experimental object is homogeneous. Let's say the experimental object are mice. So you must make sure that the mice condition are homogeneous. What if we get the experimental object that are not homogeneous? Let's say the mice are not homogeneous. Then we can control it. Let's say we can control the weight of the mice become three condition. For example, if lightweight, let's say medium weight, for example, and the high weight, for example. So that is the way how to make a local control, because we want to focus on the effect of those on the blood pressure. So, but here weight may have some influence on the blood pressure. That is why we need to control it. You can control it by grouping the weight to, let's say, light, medium, or maybe heavy weight, something like that. Right? So that is, we call it as how to control the environmental condition that have potential to affect the response of treatment. Okay. Good. That is the three basic principles in experimental design. So if everything is possible, you must consider these three basic principles before conducting experiment. Okay, what is the objective of the randomization, which is the first basic principle in experimental design? The first one is to avoid systematic error, right? Because you can remove any subjectivity methods. You can remove any subjectivity from the researchers and so on. So that one may be as a systematic error. So that there is no preference by the experimenter to apply certain treatment to certain experimental object. So that is the first objective of the randomization. The second one is to increase the validity of the conclusion, right? Because if you randomize, so there is no preference. The preference situation is can be avoided, right? So it will increase the validity of the conclusion. Because every experiment must be independent. Between first experiment to another experiment, between first run to the another run of the experiment must be independent. Okay, so how to do randomization with the development of the technology today, right? Of course, we can do randomization very easy. You can use a lottery, with lots of small papers. You give a code of the treatment, and then you apply this one at random to any experimental object. Or maybe you can use a table of random number, which is available in any statistic book, right? In any statistic book, usually in the end of the book, there will be a table of random numbers. You can use computer with the function of random. You can use calculator. There is a function of button R&D that is random actually. So you can randomize with any method. Meanwhile, regarding the second basic principles of conducting experimental design, which is replication. So the objective of having replication of an experiment is first, right? Later you will see in the calculation, it can be used to predict experimental error. Experimental error will be available in any kind of experiment. There is an experimental error, and we need the experimental error. Because if you conduct an experiment, of course, we will not have 100% correct result. So there will be some errors, but we need this error. But we don't want to have the error as very big. We want to have this experimental error as small. But of course, this one is very important in the calculation of analysis, right? So that is the first objective of having replication, to predict experimental error. The second one is to estimate the average standard error of the treatment. The standard error of the treatment here can be used for the estimation, right? So that one is the second objective. Perhaps if we don't do a kind of analysis using examples, perhaps this one will be not very clear, right? But later maybe in another course, perhaps if you learn experimental design, so you will understand more about this, right? Because this topic is as introduction for you in the first year student, right? So, but here, of course, very important objective of having replication, that is to estimate, right, the average standard error. Then, of course, to increase the precision of the conclusion, right? So, if this one is validity, actually similar with the first, the objective of randomization, to increase. If this one is validity, of course, this one is to increase the precision of the conclusion. So we need to have replication. Okay, so of course, this one will be an issue in any kind of experiment. If you want to conduct an experiment, right? Let's say you want to see the effect of dose. For example, here, let me give you some explanation, right? Okay, let's say like this. Let me make sure that I share the correct screen. Okay, let's see. You want to see the effect of dose. Okay. Let's say effect of dose to, let's say, blood pressure. So this one is kind of experiment in veterinary medicine. Okay, let's say the dose that you use, right? The dosage you use are, for example, here. Okay, so let's say here is I don't know, 2 or whatever the unit. Maybe let's say 4. Or let's say we use another number. Let's say 5. Let's say 10, 15. Okay, so on the blood pressure. Okay, so let me see what we are talking about here. So then, of course, you need to have experimental object, right? Experimental object, right here. Let's say the experimental object are mice, right? So how many mice you need? How many mice you need? So if you don't do replication, you need to have 3 mice only. Let's say mouse number 1, mouse 1, right? Mouse number 2, and then mouse number 3, right? And then this one without replication. So later on, you need to apply this dose to each mouse at random. So perhaps dose, let's say the dose of 5 to the mouse 3, let's say the dose of 10 to the mouse number 2, let's say dose of 15 to the mouse number 1. So you apply this one at random, right? So only 3 experimental objects you need. But in order to have a more valid conclusion, so it is better to have a replication, right? It is better to have replication. How many replication? Okay. So this one will be an issue. If the replication is 2, then you will have 6 mice, right? So you will have a mouse number 4, then you have a mouse number 5, you will have a mouse number 6, right? Then of course each mouse here will receive the treatment either 5 or 10 or 15 at random as well. So perhaps like this, right? Perhaps here, perhaps here, right? So each mouse, right? Each mouse here receive, each dose here will be applied to 2 mouse if the replication is 2, right? So that is why. Then the problem is how to determine the number of replication here. If the number of replication is 2, so you need to have 6 mice. If the number of replication is 3, you need to have 9 mice, and so on. And it will be related to the cost as well, the cost of your experiment, right? So several factors have influence, right? Have influence or affect to the number of replication. The first one is the level of accuracy. Smaller the difference from the hypothesis, the greater the required replication, right? So it means if you want to have more accurate result, right? So you need to have more. You need to have more replication, right? So this one is a higher accuracy means you need to have more replication. So there is no mathematical formulation how to determine the number of replication. So one of the factors is the level of accuracy. The second one is the variety of the material. How the material fluctuate, right? The more diverse, the more variability, more variance of the experimental object, you need to have more replication. So, for example, if the mice condition is not homogeneous, right? So you need to have more. Mice. But if the mice condition is very homogeneous in terms of weight, in terms of anything, then you need to have less number of replication. That one is very, very reasonable. Generally, very much determined by the cost available and time. So as I said before. So in the end, you need to consider, it is limited on the cost of your experiment, right? If you have unlimited budget, then more replication is the better. If you have more time, more replication is the better, right? And then replication will not fix the error resulting from the technical error. So replication will make sure that you will have experimental error. But more replication you have, then less experimental error you will have, like that, right? But you need to have the number of replication. So later on, you can read here when you reach the final year of your study, then you will see this kind of problem. Let's go to the next one. Meanwhile, the local control that I mentioned before, right? So to make sure that if, let's say, the experimental condition, if the experimental object or the experimental, if the environmental condition is not homogeneous, let's say you conduct an experiment in the, let's say, outdoor, in the agricultural field, in which, let's say, many factors are uncontrolled, like temperature, like wind speed, like light intensity, and then many others. So all of those you need to control. So the objective is to ensure that each treatment is tried under the same condition, right? So if, let's say, it is if the experimental object is influenced by, let's say, light intensity, right? Then you need to control the light intensity, right? Then the second one is it can increase the precision of the conclusion, similar to the number of replication, right? Then the third one is it is an effort made to make a grouping, as I informed you earlier. For example, if you cannot get a homogeneous condition of the mice, then you can do grouping, right? You can do grouping. For example, you can group the mice into lightweight, medium weight, and let's say heavyweight. So that is the way how to do a local control. Grouping is successful when the variance within the group, right? The variance of the mice within, let's say, light weight group, medium weight group, or heavy weight group is less than the variance between group, right? So this one will be efficient grouping, the way how to do a local control. Then the grouping must be perpendicular to the direction of the variation of the experimental unit. So for example, if it is related to the light condition, if you conduct an experiment in the lab in which you do an experiment in which the lab has, let's say, glass window in which the light intensity come from that direction. So make sure that maybe the closer to the window has more intensity, a bit further from the window has less intensity, and so on. So the grouping must be perpendicular to the direction of the variation, such as light intensity and so on. So requirement of the group is, of course, the group here, you will have, you will have more understanding about this when we do a kind of analysis in more complicated experiment. So the group requirement here do not interact with the treatment. We must make sure that there is no interaction between the treatment, let's say the application of dose, with let's say a weight group of the mice, something like that. Okay, so that is the objective of local control. Okay, so let's go deeper to these topics. Some terminologies related to experimental design, like a treatment. I believe you understand what I mean here. The treatment is the procedure to be applied to the experimental unit. So the treatment here, as in the previous example, let's say you want to see the effect of dosage, the effect of dose on blood pressure. So the treatment is any value of dose, either 5 unit or maybe 10 unit or maybe 15, right? So let's say the effect of dose or dosage. Let's say we want to apply 5, let's say 10 or 15 to, let's say, blood pressure, right? So here is the treatment. Either you apply 5 or maybe 10 or 15. This one is the treatment, right? Then the experimental unit, the smallest unit in the experiment to which a treatment is applied. So in this kind of experiment, the experimental object, okay, let's say mice, right? So let's say we have 12 mice. So one mouse will receive a single treatment. So one mouse will receive a single treatment. So this single mouse here is the experimental unit, right? So here the smallest unit, let's say one mouse, in this case, smallest unit in experiment to which a treatment is applied. Because later on, let's say the dose of 5 will be applied on a single mouse. Then the next one is a measurement unit, the smallest unit in the experiment in which a response is measured. So in this case, the measurement unit will be taken from the mouse. Let's say if you measure blood pressure, right? Blood pressure, then the blood pressure will be taken from each experimental unit. So the mouse is also measurement unit. So the measurement unit is also mouse. It's the same as the experimental unit. Then the next one is factor. Independent variable or covariate or control factor, which are thought to have an effect on the response. In this case, the dose is the factor. Dose is the factor, right? The factor is dose. And then the level, the values of the independent variable is factor, which were tested in an experiment. So in this case, right, the treatment, the level is this. So here, in this experiment, it has only one factor, that is dose, and the level is 3, right? the level is equal to 3. 3 level. The first level is 5, right? The second level is 10, and the third level is 15. So this one is level. So in this experiment, it has, it includes on one factor, that is dose, and the factor has 3 levels, that is 5, 10, and 15. So in this one factor experiment, so we call it as one factor experiment because in another situation, you may conduct more than one factor experiment, such as, let's say you want to see the effect of dose and types of medicine, effect of dose and types of medicine on, let's say, blood pressure. So that one is a 2 factors experiment, but here is in a single factor experiment. In a single factor experiment, the level is the same as the treatment, right? The treatment is the same as the level. Let's go to the next one. So some types of experimental design or classification of experimental design. So let me cross-check here. So, okay, let me cross-check. Okay, some classification of the experimental design, right? So we can see here, we can consider the treatment design, we can consider the environment design, and we can also learn measurement design. In the treatment design, right? So it is related to treatment we want to apply to experimental object. So the design related to what will be tested for effect. So we can design our treatment. So if we see here, there are 2 types of experimental design, treatment design. That one is single factor experiment or multi-factor experiment. As in the previous example, I have explained to you, let's say if you want to see the effect of dose on blood pressure, it is a single factor experiment. Or in another situation, you may conduct an experiment to see the effect of more than one factor. We call it as a multi-factor experiment. That is if we consider the treatment design. If we consider the environmental design or environment design, so this design is related to how, the design is related to how environmental control is carried out and how to allocate treatment to the experimental unit, right? So if you consider the environment condition, so there are 3 types of experiment. At least there are 3 types of experiment. That is completely randomized design, which is called as CRD, in which all treatment is assigned at random to all experimental object without any restriction. That is why we call it as completely randomized design. Or the second one, completely randomized block design, when you do a local control with the blocking. Here we don't do local control basically, but here we do local control. One factor as a local control. Let's say you control with regard to the weight of the mice. So we call it as completely randomized block. This one, there is a word block here. This is how to do local control. Then the third one is Latin square design. So we do double blocking. We call it as Latin square design or LSD. So this is with regard to environment design. So another classification of the experimental design is regarding the measurement design. It is related to how to measure the response treatment. So perhaps let me use a different word. Let's say, just use this one, so the better one. Okay. So please do necessary corrections so that you can. It will be easier to understand. Okay. It is related to how to measure the response to treatment. Okay. Let me maximize again. Okay, so with regard to measurement design, we can see here whether the response, or the response is qualitative in which perhaps only level like or maybe scoring, right? If I mean the result of the measurement is not in terms of numbers, only level, right? It can be in terms of scoring. Maybe for example, if we talk about maturity of fruit, right? Maybe level 1, level 2, level 3 on this ordinal scale, right? Not in terms of numbers or measurement, right? Let's say fruit quality. Food quality, let's say low quality, medium quality, and high quality. So the one is qualitative. Meanwhile, the most common measurement you obtain from an experiment is quantitative. Quantitative is a kind of measurement. You measure length, weight, blood pressure, temperature, volume, and so on. So it is related to the measurement design, whether the measurement is qualitative or quantitative. Okay. So until this slide, let me know if you have any questions. Okay, let me know if you have any questions until this slide. Is anything clear?
All clear, sir. No questions.
Thank you. Let's go to the next one. So I believe you will feel this topic perhaps if not this semester, maybe when you reach your final year of your study, because in that time, so you will do an experiment for your final year project. Okay, meanwhile, this one is the types. If the previous one is the classification of experimental design regarding treatment design or environmental design or maybe measurement design. But here we talk about the types of experimental design. One of them is overlap with the previous one, with the previous classification. So for example, here, if you talk about treatment design, there is a single factor or multi-factor experiment. So it is actually here, type 1, right? Type 1 is single factor experiment. It is similar to the classification of this, right? Because this one is single factor or multi-factor. So let's go back here. Single factor experiment, right? If you see the treatments tested are the level. Look at this. The treatment is the same as the level of the factor. If you, in the previous one, if you talk about the dose, right? So we conduct an experiment, in the previous one, to see the effect of dose on blood pressure. There are 3 levels of dose that we want to apply, 5, 10, or 15. So this level are the treatment itself for a single factor experiment. Later on, in experiment involving more than one factor, the treatment is the combination of levels of the factors that you use in that experiment. Okay, let's go back here. Okay, so again, the treatment tested are the level of that factor, right? So here, in the single factor experiment, right, you can apply the environment design. So because here, the types of experiment is actually combination of the experimental design classification. So let's say in an experiment, so you can talk about what is the treatment design. Okay, let's say single factor. If the treatment design is single factor, what is the environmental design? What is the environment design? Okay, single factor of the treatment design, and we want to apply CRD. It means the treatment design is single factor, and then the environment design is completely randomized design. And what is the measurement design? Okay, I want to measure both qualitative and quantitative. It is fine, because in a single experiment, you may have more than one measurement. So basically, in designing your experiment, you combine all of this. Right, you combine all of this. You need to determine what is the treatment design. You need to determine what is the environment design, and you need to determine what is the measurement design. Right, as you can see here. Right, so the treatment design is single factor. Then what is the environment design? You can apply CRD. Right, you can apply CRBD. There is a block here. I have explained to you before. And then you can also apply double blocking. Let's say Latin square design, right? Well, then the design name here, of course, the measurement design is not included here because it is related to the measurement only, right? Then the name of the design here is single factor CRD. Single factor CRD. Here, single factor CRBD, completely randomized block design. Here, single factor LSD, or single factor Latin square design. So that is the way how to identify the design of your experiment. Meanwhile, if you conduct more than one factor experiment that later on we call it as factorial design, so it is experiment involving more than one factor. Let's say the treatment design is factorial. How many factors you use? So in the factorial design, so for example here, let's say I want to see the effect of dose, right? Here the dose is, let's say 5, 5, let's say 10 or 15, and let's say types of medicine, right? Let's say type of medicine here, let's say only A and B. To, let's say, blood pressure. So dose has 3 levels, right? Here has 3 levels. And types of medicine has 2 levels only, 2 levels. Then when we combine these 2 factors, then of course later on you need to combine. Let's say the dose. Let's say the dose of 5. So let me just put here. Okay, dose here is medicine, or the other way around. No problem. Right? The dose is 5, 10, or 15. The medicine is A or B. So you need to combine the dose of 5 of medicine A, the dose of 5 of medicine B, the dose of B of medicine A, the dose of 10 of medicine B, the dose of 15 of medicine A, the dose of 15 of medicine B. So the combination of this is as a treatment. 5, and let's say 5A, 5B, 10A, 10B, 15A, 15B. So that is the combination. So as you can see here, the treatment tested is a combination of levels. Combination of levels of 2 factors or more. In this case, 2 factors only. If 3 factors, you must combine the levels of all the 3 factors. So in this case here, let's say factorial CRD, right? If you apply CRD in environmental design, in environment design. Here, factorial CRBD. Here, factorial LSD and so on. So that is, again, the way how to identify or the way how to determine the types of your experiment. Okay, let's go to the next. So this is the experimental layout. So as an illustration, so perhaps by having this one, so you can have more understanding about let's say the way how to conduct an experiment. Okay, let's see here. Experimental layout is a layout of the treatment for all experimental objects in the field. Again, the field here is in very general meaning. The experiment layout varies between types of experimental design. Again, the experiment layout varies between types of experimental design. So it depends on your design. In general, the steps taken to build an experimental layout are as follows. First, you need to know what is the number of treatment, right? So it is related to how many factors, how many levels of each factor, and so on. So number of treatment to be tested. And then to prepare the experimental unit to be used, right? For example, the number of T treatment, let's say we have a T treatment and R replication. Later, previously we talked about replication. So that you will know how many experimental object or how many experimental unit you use. Because if the number of treatment is 3, let's say 3, and the number of replication is 3, so what you need to have is 9 experimental objects, right? Then prepare as many as T times R unit. of the experiment or experimental unit. So if the experimental object is mice, then you need to prepare 9 mice because 3 times 3 and so on. And then we give the experimental unit a number. Give the experimental unit a number. For example, 1, 2, 3, and so on. Assign number to each experimental unit. I think let me give you better words. Assign a number to each experimental unit. Okay, to each experimental unit. I think this one will be the better word, right? Assign a number to each experimental unit. So maybe if the experimental object is mice, then you can assign 1, 2, 3, 4 until 9 or until 12, right? Okay. Then randomize the treatment to each experimental unit. So we need to randomize the treatment to the experimental unit at random. You can use calculator or random number table, or we can generate a random number using software and so on. Actually, even you can use a Microsoft Excel. Correct. So later I will explain to you. So for example, here, let me explain to you maybe how to understand about this experimental layout. Okay, let me just give you an illustration here. Okay, so that at least you can imagine later on if you conduct an experiment, you can imagine how to arrange the layout of this experiment. Let's say we want to see the effect. The same example, effect of dose. Let's say dose on blood pressure. Let's say blood pressure. Let's say here is the factor. The factor is dose. Let's say we use a 3 level of dose. Let's say 5, 10, and 15. Let's say the number of replication is equal. Let's say we use a 4 replication. Each treatment is applied to experimental object 4 times. So in this case, you need to have 3 times 4. So the number of experimental object you use, or experimental unit you use, right? Unit or object is equal to 3 times 4, which is equal to 12. So let's say if we arrange a layout like this, right? Okay, let's say here we arrange become, let's say 12, right? Okay, let's say here 1, 2, 3. So each square here represent one mouse, right? So let's say here is actually let's say assume that the experimental object is mice, right? So each square here represent one mouse, right? So later on you will have here, right? You will have the dose of 5 will be applied to 3 mice. Will be applied to 4 mice. So let's say here 5, 5, 5, 5. Why? Because replication is 4. Then you will the dose of 10 will be applied to 4 mice as well. Okay, 4, 4, 4. And then the dose of 15 will be applied to 4 mice as well. 15, 15, 15, 15. Then here, right, let's say you assign here, let's say number 1, number 2, and so on to this one, right? Let's say this one is let's say mouse number 1, mouse number 2, mouse number 3, mouse number 4, number 5, number 6, number 7, number 8, right? Number 9, number 10, number 11, number 11, number 12. So this one is a mice number. Then you need to apply at random. You need to assign at random each treatment to the experimental unit. Let's say those of the first 5 here will be applied at random, or perhaps the first here will be applied here. Okay, so mouse number 6 will receive dose of 5. Okay, let's say the second 5 here. Okay, maybe it goes here at random. This one is also 5. And then the third 5 here goes here. It's fine. So this one should be at random. And then the fourth 5 here maybe goes here. So this one is also at random. Then it's done. Then we need to assign the first dose of 10, or maybe it goes here. It's fine, right? Then the second 10 here goes here. Let's see. Let me use a different color, perhaps. Let me use different color. Let's say yellow. Okay. Let's say 10 here. Maybe it goes here. Then the second 10 here goes here at random, and then the third 10 here goes here, is fine, and then the fourth number 10 here, let's say, goes here at random. Okay, this completed, and then the last one is, let's say, the dose of 15 is applied. Maybe the first 15 goes here, is okay. The second 15 here goes here, fine. The third 15 goes here. Then the fourth 15 goes here. Then, as you can see here, each experimental unit receive a treatment. Okay, so that is the experimental layout. Yeah, so this is the layout of the experiment. Then you can then later on you can take the measurement. Okay, so that is the experimental layout. Okay, let's see here a single factor CRD as an illustration. Okay, this is the simplest experiment you can do. Yeah. One factor, single factor, and completely randomized design. So that is actually the way how to conduct this experiment. So what I explained to you here, it is how to conduct a single factor experiment, single factor CRD, right? So exactly like what I explained to you here. So by my explanation here, I believe you can have more understanding rather than to read perhaps this kind of sentences. Okay, so I think that one is very clear. In the single factor CRD, the characteristic of the design, the treatment is applied is, the treatment applied is the level of the only factor, because only one factor experiment. Okay. The second one is the factor beyond the treatment are conditioned similarly or homogeneous. Right. I think this one is I think better to refer to my previous explanation. So the experimental units are homogeneous or assumed to be homogeneous. If you use mice, the mice should be as homogeneous as possible. Okay, so this is I think the same illustration, so I will not use this one because this is exactly similar to what I have explained to you with the previous example. So exactly the same, right? Okay, and then in terms of analysis, right? So in terms of analysis, we must start with a model, right? So this one is for your information only. What I mean here is this is as an introduction to you, right? Perhaps you will get confused or maybe not really understand with all the symbol here, but let me try to explain to you as best as I can, right? Because it involves a linear model, right? So the why here is, in the experiment, we need to symbolize the response variable, the treatment, the errors, and so on in a mathematical symbol, right? So, for example, here, the response or the measurement you obtain is symbolized by the Y. This is the response. Let's say Yij. So, I will represent something, J will represent another thing, right? So, Yij, which is the measurement, is equal to overall mean plus This is the treatment effect, the ith treatment effect. Look at this here, the effect of ith treatment, the effect of dose here, effect of, let's say, dose of 5, effect of dose of 10, effect of dose of 15, right? Effect of, we call it as effect of the ith treatment. And then here is something that we do not know beyond the treatment we apply. Of course, many factors have influence on the blood pressure. One of them is dose. Another thing, many. Of course, beyond our experiment, it will go to the error or experimental error, right? So Yij is equal to overall mean plus the treatment effect of the ith treatment plus the error of the ith treatment and jth replication. Look at this, observation of ith treatment and jth replication, right? Or you can also rewrite this linear model as Yij, which is the response, is equal to, if you see here, the ith treatment effect, ith treatment mean plus the what we call the experimental error. So basically, this one, mu plus tau I is equal to mu I. That is why the left and the right are the same. So that is the linear model. What is the hypothesis? The hypothesis is all treatment give the same effect, right? All you can see here, all treatment give the same response mean. Either dose of 5 or dose of 10 or dose of 15 will give the same response, will give you the same response mean. No difference of the effect of dose on the response. So whether you apply a dose of 5 or dose of 15 or dose of 10 will give you the same result. So that is in the null hypothesis. So of course, you expect to reject the null hypothesis because you expect that the dose has different effect, right? The dose of 5 or 10 or 15 will have a different effect. That is in the alternative hypothesis. But in the null hypothesis, we assume that all give the same response mean, right? So that is in the linear model. Of course, we will not go to very deep analysis like this, but this one is as an introduction to you that all of those experimental design will have some mathematical formulation in terms of linear model, in terms of analysis, and so on. Okay, so this is after you conduct an experiment, you can tabulate the obtained measurement, become like this, for example. So maybe you can give a code of the treatment. Let's say treatment here, let's say dose of 5, dose of 10, or dose of 15, right? This is replication number 1, 2, 3, or 4, right? Depends on the number of replication. And then here is the result of the first measurement. First treatment, let's say dose of 5, replication number 1, you put here. So in our previous whiteboard, so here, this is let's say this is a first replication of dose 5. So you will have a measurement here. So a mouse, you apply dose of 5 and then you measure the blood pressure, right? So this is the response variable. So that if you go here, so here is the blood pressure you obtain from a mouse. You apply dose of 5, the first replication. So the first mouse. So this is the blood pressure. This is a blood pressure you get from the second replication of the same treatment of dose of 5 and so on. Right? So again, Y11, Y12, this one represent Yij. Ith treatment of jth replication. And then from this table, of course, you will be able to calculate the variance of each of each treatment. Let's say S1 square is the variance of the first treatment, S2 square is the variance of the second treatment, and so on. So the way how to calculate the variance is just like what we have learned in the previous lectures. So that is the measurement, the formula. So you can measure from each treatment here. And of course, you can, you will be able to calculate easily the total of the ith treatment. So for example here, Y1 dot is actually the total or the summation of Y11, Y12, Y13, and so on until the last one. So we call it as Y1 dot. Here, sorry. The second one is Y2 dot, is the summation of this, and so on. And you can, of course, make this kind of summary. Okay, then the next one is after you make a summary in terms of tabular representation like in the previous slide, then of course you can do all of this calculation, because this one is the total, right? Y1 dot, like what you obtain here, Y1 dot, Y2 dot, and so on. So we call it as the treatment total. Then later you can calculate the average. Okay, this is Y bar 1 dot. Okay, again this is actually Y bar 1 dot. So this one is Y bar 2 dot, Y bar 3 dot, and so on. Right, Y bar E dot. So the total divided by the number of replication. The total you obtain here divided by the number of replication, and this is the variance of the ith treatment that you obtained previously. So this one is S1 square, S2 square, and so on. Okay, then from here you can create graphical representation of the above summaries, and we can see the pattern of the data distribution of each treatment. So you can also create a box plot of each treatment, right? So then from this graphical representation, you can see the trend of which the treatment give a high and low response, and the comparison of variability between treatment. Later I will show you an illustration about this. Okay, let's go to the next one. So this is an example. Okay. Let's say a postgraduate student in IPB University conducted an experiment to see the effect of dosage of fertilizer N fertilizer on corn production or maize, corn or maize production. So sometimes you call it as maize, sometimes you call it as corn. The dosage of the N fertilizer, the dosage of N fertilizer applied were 0, without any fertilizer, or 1 kilogram per hectare, or the third level is 200 kilogram per hectare with 4 application. So as you can see here, the level are 3, 0, 100, and 200 with 4 application. Very similar to the example that I explained to you with the effect of dosage on blood pressure. The experimental unit is a plot, because it is in the field experiment, right? It's a plot of the length measuring 1 meter times 4 meter square. Okay, 1 times 4 meter, right? This is in one plot. Okay, so perhaps if you go to, for example, agricultural field, right? It is divided into grids like this, right? So here, for example, so one plot here, this one is 1 times 4 meter square. Okay, 1 times 4 meter. Okay, so okay, let me see here. The experiment was carried out in experimental field of the IPB Darmaga campus, in which the general condition of the experimental field was relatively homogeneous. All factors other than dosage of the fertilizer, such as varieties, seed health, and then wind speed, tillage, spacing, period of and frequency of spraying, and so on, are homogeneous. So the response observed was the maize or corn production per plot. Let's say kilogram per plot, because this one is 1 times 4 meter square. So the summary of the above experiment is as follows. The factor is fertilizer N, fertilizer N dose, right? N fertilizer dosage. Let's say we call it as to simply mention about the dosage of this fertilizer, because we use only one fertilizer. Let's just put as dosage. And then the treatment or the level is 0 kilogram per hectare, 100 kilogram per hectare, or 200 kilogram per hectare. Replication is 4 times. So the response will be maize production per plot, right? So the design here, one factor CRD, or completely randomized design. Okay, so you need to have 3 times 4, 12. So 12 experimental plot. So maybe let me just close this one first. So what you need is this kind of layout. Let me just put here. So the layout will be like similar to this, right? Let's say here. So you need to have here 3 times 4. So it is equal to 12. Let's say like this, right? Okay, 3. Okay, let's say times 4. So similar to this perhaps, right? So here, one plot here. This one is, let's say, 1 times 4, right? Meter square. So in the total, you need to have 12 plots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here, because this one is 3 times 4. Okay, so this is one factor CRD. So the layout perhaps like this. So maybe slightly different from what I prepared. The layout. So not 3 times 4. Actually, will be the same. So let's say in the first one, the first plot here receive dose of 0. This is the first one, dose of 0. This one, the second plot, receive dose of 100 kilogram per hectare. Okay, the third plot receive, let's say 0 again. The third plot, the fourth plot receive the 200. This one also received 200 and so on. So we assign this one at random to each experimental plot, right? Okay, and then after sometimes you, let's say after a few months, perhaps, or maybe after a few weeks, you measure the response, or maybe a few months, right? So you apply the dosage of the fertilizer on each plot with a different value, either 0, 100, or 200 on this 12 field. And then after sometimes, let's say perhaps 3 months for the maize production, then you measure the yield, the yield or the production of the maize production. Let's say from here, from the first one, so it gets 20 kilogram per hectare. On the second one, remember that this summary is different from this layout. So this is a table of summary, right? This is the tabulation of response data. This is the layout, so it is different, right? So let's say this one, after summarizing what you obtain from here, you create this table. Okay. Okay, so the next one is maybe you calculate the treatment total, total response, treatment means, right? So here, if you see here for the 0, the total is 86. Okay, let's say 0. Look at this, the total is 20 plus 22 plus 21 plus 23. So the total is 86, right? So you can see here 86. For the 0, for the 100 kilogram per hectare, the total is 97. For the 200 kilogram per hectare, the total is 113, right? So 113, for example, here is obtained from here. 50 times 51, 30 plus 31 plus, let's say 25 plus 27. So the total here is 113. Okay, let's see. Let me go here. 113. So after dividing it by 4, you will have this 21.5. This is a treatment means. You divide it by the number of replication. Then the variance you obtain from the previous data you obtain here. And you can see here, maybe you can get a plot here. So you can see here that the dose of 200, for example, give you the highest yield. Yeah, the dose of 200 kilogram per hectare. So you can see here is the highest, right? So this is a kind of experiment. Of course, there is a way how to do a statistical analysis, but here let's use exploration approach how to analyze this data. Or maybe you can see the box plot here, right? So you can see here. So the result in general here is the highest if you apply 200 kilogram per hectare dose, right? But the variability is quite high because the length of the box plot here is the longest box plot here. This one is quite stable, but the result is not quite high, and so on. So you can conclude from the analysis what is the response mean between the treatment, so you can compare between treatment means. You can determine which treatment give the highest response. Of course, this one. The treatment of 200 kilogram per hectare give the highest response. What about the error variance between treatments? Which treatment contribute the variability of the error? So we see here if you apply the dose of 200, give the highest variability. The variability is the highest. But the dose of 0, I mean without any fertilizer applied, so the variability is the smallest. So that is actually the way how to conduct a simple experiment, right? Of course, more detail about this kind of experiment, many types of design of the experiment. You can do a statistical analysis to compare between treatments using BNT, let's say, and many other methods. Actually, this is as the introduction, right? So you can obtain, perhaps later on, I don't know in which semester, if there is a course which is called as analysis or an experimental design course. So maybe you can take that course. That one is very good to learn more about the way how to conduct an experiment. So that is the end, the last slide of this lecture today. So let me know if anything is not clear. So please. Is anything clear?
All clear, sir.
Okay, let me stop the recording so later I can